biology tutorials. In today's video, we will be doing the live reading of the chapter Work and Energy. This is chapter number 10 of class 9 science taken from NCERT. I hope the screen is visible to everybody. This is the 10th chapter of the reading one. If you are interested in hearing the audio of the first 9 chapters, you can come to the playlist of my channel, which is named as Grade 9 Audiobook of Science. So, there you can find all the chapters. And whenever you will hear to the audio of this chapter, I would request you to share it with your friends so that each one could take the benefit of revising. These audiobooks are quite helpful once you are done with the chapters. So you can use the earphones or headphones, whatever is convenient to you, and you can hear the line by line audio so that in case your teacher is emphasizing in between questions in any test or assessment, you will always be benefited. So here we go with the reading of chapter 10, Work and Energy. In the previous few chapters, we have talked about ways of describing the motion of objects, the cause of motion and gravitation. Another concept that helps us understand and interpret many natural phenomena is work. Closely related to work are energy and power. In this chapter, we shall study these concepts. All living beings need food. Living beings have to perform several basic activities to survive. We call such activities life processes. The energy for these processes comes from food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling, and running. Activities that are strenuous require more energy. Animals too get engaged in activities. For example, they may jump and run. They have to fight, move away from enemies, find food, or find a safe place to live. Also, we engage some animals to lift weights, carry loads, pull carts, or plow fields. All such activities require energy. Think of machines. List the machines that you have come across. What do they need for their working? Why do some engines require fuel like petrol and diesel? Why do living beings and machine need energy? So here we go with the reading of 10.1 work. What is work? There is a difference in the way we use the term work in day to day life and the way we use it in science. To make this point clear, let us consider a few examples. 10.1.1 Not much work in spite of working hard. Kamali or Kamali is preparing for examinations. She spends a lot of time in studies. She reads books, draws diagrams, organizes her thoughts, collects question papers, attends classes, discusses problems with her friends, and performs experiments. She expends a lot of energy on these activities. In common parlance, she is working hard. All this hard work may include very little work if we go by the scientific definition of work. You are working hard to push a huge rock. Let us say the rock does not move despite all the effort. You get completely exhausted. However, you have not done any work on the rock as there is no displacement of the rock. You stand still for a few minutes with a heavy load on your head. You get tired. You have exerted yourself and have spent quite a bit of your energy. Are you doing work on the load? The way we understand the term work in science, work is not done. You climb up the steps of the staircase and reach the second floor of a building just to see the landscape from there. You may even climb up a tall tree. If we apply the scientific definition, these activities involve a lot of work. Hi, Dave. In day to day life, we consider any useful physical or mental labor as work. Activities like playing in a field, talking with friends, humming a tune, watching a movie, attending a function are sometimes not considered to be work. What constitutes work depends on the way we define it. We use and define the term work differently in science. To understand this, let us do the following activities. Hi Dave, welcome to my channel. Please share the present live with your friends so that each one can take the benefit. Activity 10.1. We have discussed in the above paragraphs a number of activities which we normally consider to be work. Let's flip on to the next page. This is 114 page of your NCERT. In day-to-day life, for each of these activities, ask the following questions and answer them. 1. What is the work being done on? Second, what is happening to the object? Third, who, what is doing the work? So we are on the next topic, 10.1.2, Scientific Conception of Work. Dave, I have also done the recording of Science NCERT for class 10th. In case you have not tried listening this, you can come to the playlist and do listen the audio once. I have recorded the complete explanation of the chapter life processes, and explanation of the heredity chapter also is there on my channel. So whenever you'll be free, just have a glance at it. Thank you. To understand the way we view work and define work from the point of view of science, let us consider some situations. Push a pebble lying on a surface. The pebble moves through a distance. You exerted a force on the pebble and the pebble got displaced. In this situation, work is done. A girl pulls a trolley and the trolley moves through a distance. The girl has exerted a force on the trolley and it is displaced. Therefore, work is done. Lift a book through a height. To do this, you must apply a force. The book rises up. There is a force applied on the book and the book has moved. Hence, work is done. A closer look at the above situations reveals that two conditions need to be satisfied for work to be done. 1. A force should act on an object, and 2. The object must be displaced. If any of the above conditions does not exist, work is not done. This is the way we view work in science. A bullock is pulling a cart, the cart moves. There is a force on the cart and the cart has moved. Do you think that work is done in this situation? Activity 10.2. Think of some situations from your daily life involving work. List them. Discuss with your friends whether work is being done in each situation. Try to reason out your response. If work is done, what is the force acting on the object? What is the object on which the work is done? What happens to the object on which work is done? We are coming to the activity 10.3. Thank you, Dave. Uh, so we are beginning with the reading of the activity 10.3. Think of situations when the object is not displaced in spite of a force acting on it. Also think of situations when an object gets displaced in the absence of a force acting on it. List all the situations that you can think of for each. Discuss with your friends whether work is done in these situations. 10.1.3, Work done by a constant force. How is work defined in science? To understand this, we shall first consider the case when the force is acting in the direction of displacement. Let a constant force F acts on an object. Let the object is displayed through the distance S in the direction of the force. Figure 10.1. Let W be the work done. We define work to be equal to the product of the force and displacement. So that is why work done is equals to force into displacement. That will become W is equals to F into S. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. In equation 10.1, if F is equals to 1 Newton and S is 1 meter, then the work done by the force will be 1 Newton meter. Here the unit of work is Newton meter or joule. Thus, 1 joule is the amount of work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Look at equation 10.1 carefully. What is the work done when the force on the object is zero? What would be the work done when the displacement of the object is zero? Refer to the conditions that are to be satisfied to say that work is done. Example 10.1. A force of 5 Newton is acting on an object. The object is displayed through 2 meter in the direction of the force, figure 10.2. If the force acts on the object all through the displacement, then work done is 5 Newton into 2 meter is equals to 10 Newton meter or 10 joule. Question 1. A force of 7 Newton acts on the object. The displacement is say 8 meter. in the direction of the force, figure 10.3. Let us take it that the force acts on the object through the displacement. What is the work done in this case? Consider another situation in which the force and the displacement are in the same direction. A baby pulling a toy car parallel to the ground as shown in figure 10.4. The baby has exerted a force in the direction of the displacement of the car. In this situation, the work done will be equal to the product of the force and the displacement. In such situations, the work done by the force is taken as positive. Consider a situation in which an object is moving with a uniform velocity along a particular direction. Now, a retarding force F is applied in the opposite direction. That is, the angle between the two directions is 180 degree. Let the object stop after a displacement S. In such a situation, the work done by the force F is taken as negative and denoted by the minus sign. So the work done by the force is F into minus S or minus F into S. It is clear from the above discussion that the work done by the force can either be positive or negative. To understand this, let us do the following activity. Activity 10.4. Lift an object up. Work is done by the force exerted by you on the object. The object moves upwards. The force you exerted is in the direction of displacement. However, there is the force of gravity acting on the object. Which one of these forces is doing positive force? Which one is doing negative work? Give reasons. Work done is negative when the force acts opposite to the direction of displacement. Work done is positive when the force is in the direction of displacement. Example 10.2. A porter lifts a luggage of 15 kg from the ground and puts it on his head 1.5 meter above the ground. Calculate the work done by him on the luggage. Solution. Mass of luggage is 15 kg, that is m. Displacement s is 1.5 meter. So work done will be equal to W is equal to F into S, that is milligram per second. So the answer will come in joules, 225 joules. So work done is 225 joules. In tech questions, when question number 1, when do we say that work is done? Question number 2, write an expression for the work done when a force is acting on an object in the direction of its displacement. Question number 3, define 1 joule of work. Question number 4, a pair of bullocks exert a force of 140 Newton on a plow. The field being plowed is 15-meter long. How much work is done in plowing the length of the field? 10.2, energy. Life is impossible without energy. The demand for energy is ever increasing. Where do we get energy from? The sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. We can also get energy from the nuclei of atoms, the interior of the earth, and the tides. Can you think of other sources of energy? Activity 10.5. A few sources of energy are listed above. There are many other sources of energy. List them. Discuss in small groups how certain sources of energy are due to the sun. Are there sources of energy which are not due to the sun? The word energy is very often used in the daily life, but in science we give it a definite and precise meaning. Let us consider the following examples. When a fast moving cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object when raised to a certain height gets capacity to do work. You must have seen that when a raised hammer falls on a nail placed on a piece of wood, it drives the nail into the wood. We have also observed children winding a toy, such as a toy car, or when the toy is placed on the floor, it starts moving. When a balloon is filled with air and we press it, we notice a change in its shape. As long as we press it gently, it can come back to its original shape when the force is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound. In all these examples, the object acquires through different means the capacity of doing work. An object having a capacity to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. How does an object with energy do work? An object that possesses energy can exert a force on another object. When this happens, energy is transferred from the former to the latter. The second object may move as it receives energy and therefore do some work. Thus, the first object had a capacity to do work. This implies that an object that possesses energy can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is therefore the same as that of work, that is, joule, denoted as capital J. 1 J is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule kJ is used. 1 kJ is equals to 1000 joules. Next, forms of energy. Luckily, the world we live in provides energy in many different forms. The various forms include mechanical energy, potential energy, plus kinetic energy, heat energy, chemical energy, electrical energy, and light energy. Think it over. How do you know that some entity is a form of energy? Discuss with your friends and teachers. James Prescott Joule was an outstanding British physicist. He is best known for his research in electricity and thermodynamics. Amongst other things, he formulated a law from the heating effect of electric current. He also verified experimentally the law of conservation of energy and discovered the value of the mechanical equivalent of heat. The unit of energy and work called joule is named after him. 10.2.2 Kinetic Energy Activity 10.6. Take a heavy ball, drop it on a thick bed of sand. A wet bed of sand would be better. Drop the ball on the sand bed from height of about 25 centimeter. The ball creates a depression. Repeat this activity from heights 50 centimeter, 1 meter and 1.5 meter. Ensure that all the depressions are distinctly visible. Mark the depressions to indicate the height from which the ball was dropped. Compare their depths. Which one of them is deepest? Which one of them is shallowest? Why? Why has what has caused the ball to make a deeper dent? Discuss and analyze. Activity 10.7. Set up the apparatus as shown in figure 10.5. Place a wooden block of known mass in front of the trolley at a convenient fixed distance. Place a known mass on the pan so that the trolley starts moving. The trolley moves forward and hits the wooden block. Fix a stop on the table in such a manner that the trolley stops after hitting the block. The block gets displaced. Note down the displacement of the block. This means work is done on the block by the trolley as the block has gained energy. From where does this energy came? Repeat this activity by increasing the mass on the pan. In which case is the displacement more? In which case is the work done more? In this activity, the moving trolley does work and hence it possesses energy. A moving object can do work. An object moving faster can do more work than an identical object moving relatively slow. A moving bullet blowing wind, a rotating wheel, a speeding stone can do work. How does a bullet pierce the target? How does the wind moves the blade of the windmill? Objects in motion possess energy. We call this energy as the kinetic energy. A falling coconut, a speeding car, a rolling stone, a flying aircraft, flowing water, blowing wind, a running athlete, etc. possess kinetic energy. In short, kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of an object increases with its speed. How much energy is possessed by a moving body by virtue of its motion? By definition, we say that the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. We are moving to the next page. This is page number 118 of your NCERT, chapter number 10. Let us now express the kinetic energy of an object in the form of an equation. Consider an object of mass m moving with a uniform velocity u. Let us now be displaced through a distance s when a constant force F on it in the direction of its displacement. From equation 10.1, the work done W is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let a be the acceleration produced. We studied three equations of motion, the relation connecting the initial velocity u and the final velocity v of an object moving with a uniform acceleration a, and the displacement s is v square minus u square is equals to 2as. This gives s is equals to v square minus u square upon 2a. From section 9.4, we know f is equals to ma. Thus, using equation 10.2 and 10.1, we can write the work done by a force. F is W is equals to ma bracket v square minus u square upon 2a. So W will become half m bracket v square minus u square. If the object is starting from its stationary position, that is u is equals to 0, then W will become half mv square. It is clear that the work done is equal to the change in the kinetic energy of an object. If u is 0, work done will be half mv square. Thus, kinetic energy possessed by an object of the mass m and moving with a uniform velocity v is Ek is equals to half mv square. Example 10.3, an object of mass 15 kg is moving with a uniform velocity of 4 meter per second. What is the kinetic energy possessed by the object? So solution of it is mass of the object m is 15 kg, velocity is 4 meter per second. So from equation 10.5, Ek is equals to half mv square, that will give you 120 joules. The kinetic energy of an object is 120 joules. 10.4. What is the work to be done to increase the velocity of a car from 30 km per hour to 60 km per hour if the mass of the car is 1500 means 1500 kg. Solution: mass of the car m is 1500 kg. Initial velocity of the car u is 30 km per hour. So after putting the values, you will get the answer as 25 by 3 meter per second. Similarly, the final velocity of the car is 60. So v will become 50 by 3 meter per second because the earlier answer was in kilometer. Therefore, the initial kinetic energy of the car is EKI is equals to half mu square. So after putting the values, you'll get 156250 by 3 joules. The final kinetic energy of the car will be 625000 by 3 joules. Thus the work done is equals to the change in kinetic energy. So it will be EKF minus EKI, that will give you 156250 joules. In text questions, question number 1, what is the kinetic energy of an object? 2, write an expression for the kinetic energy of an object. The kinetic energy of an object of mass m moving with the velocity of 5 meter per second is 25 joules. What will be its kinetic energy when its velocity is doubled? What will be its kinetic energy when its velocity is increased 3 times? So next one, 10.2.3, potential energy. Activity 10.8. Take a rubber band, hold at one end and pull from the other. The band stretches. Release the band at one of the ends. What happens? The band will tend to regain its original length. Obviously, the band had acquired energy in its stretched position. How did it acquire energy when stretched? Activity 10.9. Take a slinky as shown below. Ask a friend to hold one of its end. You hold the other end and move away from your friend. Now you release the slinky. What happened? How did the slinky acquire energy? Did it stretched when stretched? Would the slinky acquire energy when it is compressed? Activity 10.10. Take a toy car, wind it using its key, place the car on the ground. Did it move? From where did it acquires energy? Does the energy acquired depends on the number of windings? How can you test this? Activity 10.11. Lift an object through a certain height. The object can now do work. It begins to fall when released. This implies that it has acquired some energy. If raised to a greater height, it can do more work and hence possesses more energy. From where did we it get the energy? Think and discuss. In the above situation, the energy gets stored due to the work done on the object. The energy transferred to an object is shared as potential energy if it is not used to cause the change in the velocity or speed of the object. You transfer energy when you stretch a rubber band. The energy transferred to the band is its potential energy. You do work with while winding the key of a toy car. The energy transferred to the spring inside is stored as potential energy. The potential energy possessed by the object is the energy present in it by virtue of its position or configuration. Activity 10.12. Take a bamboo stick and make a bow as shown in figure 10.6. Place an arrow made of a light stick on it with one end supported by the stretch string. Now stretch the string and release arrow. Notice the arrow flying off the bow. Notice the change in the shape of the bow. The potential energy stored in the bow due to the change of the shape is then used in the form of kinetic energy in throwing of the arrow. 10.6 is showing you an arrow and stretch string on the bow. So we are on page number 120 and our heading is 10.2.4. I hope the screen is visible to everybody. Potential energy of an object at a height. An object increases its energy when raised through a height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is the gravitational potential energy. The gravitational potential energy of an object of a point above the ground is determined as the work done in raising it from the ground so that point against the gravity. It is easy to arrive at an expression for the gravitational potential energy of an object at a height. Consider an object of mass m, let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of an object mg. The object gains energy equal to the work done on it. Let the work done on the object against the gravity be w. That is, work done is equals to force into displacement. So it can also be written as mgh. Since work done on the object is equal to mgh and energy equal to mgh units is gained by the object, thus this is the potential energy or EP of the object. So EP will be equal to mgh. More to know, the potential energy of an object at a height depends on the ground level or the zero level you choose. An object in a given position can have a certain potential energy with respect to one level and a different value of potential energy with respect to another level. It is useful to note that work done by the gravity depends on the difference in vertical heights of the initial and final positions of the object and not on the path along with which the object is moved. Figure 10.8 shows a case where a block is raised from position A to B by taking two different paths. Let the height AB is equals to h. In both the situations, the work done on the object is mgh. Example 10.5. Find the energy possessed by an object of mass 10 kg when it is at a height of 6 meter above the ground. Let g is equals to 9.8 meter per second square. So its solution is mass of the object is m 10 kg, displacement or height is 6 meter, acceleration due to gravity is 9.8 meter per second square. So from equation 10.6, potential energy is mgh and its value will come out to be 588 joules and the potential energy is 588 joules. Example 10.6. An object of mass 12 kg is at a certain height above the ground. If the potential energy of the object is 480 joules, find the height for at which the object is with respect to the ground. Given g is equals to 10 meter per second square. So mass is given as 12 kg, potential energy is 480 joule. We know that EP is equals to mgh. So putting the values here, we can calculate h as to be 4 meters. The object is at the height of 4 meters. 10.2.5 are various energy forms interconvertible. Can we convert energy from one form to another? We find in nature a number of instances of conversion of energy from one form to another. Activity 10.13. Sit in small groups, discuss the various ways of energy conversion in nature. Discuss the various questions in your group, like how do green plants produce food? Where do they get their energy from? Why does the air move from one place to another? How are vacuums such as coal and petroleum formed? What kind of energy conversion sustain the water cycle? Activity 10.14. Many of the human activities and the gadgets we use involve conversion of energy from one form to another. Make a list of such activities and gadgets. Identify in each activity or gadget and the kind of energy conversion that takes place. So we are still on the right side of page number 121. After this, we are left with two more pages and then the summary will be there. So 10.2.6 Law of Conservation of Energy. In activities 10.13 and 10.14, we learned that the form of energy can be changed from one form to another. What happens to the total energy of a system during or after the process? Whenever energy gets transformed, the total energy you can have a glance at it. So here we start with 10.2.6 Law of Conservation of Energy. In activities 10.13 and 10.14, we learned that the form of energy can be changed from one form to another. What happens to the total energy of a system during or after the process? Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created or destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valid in all the situations and for all kinds of transformations. Consider a simple example. Let an object of mass m be made to fall freely from a height of h. At the start, the potential energy is mgh and the kinetic energy is zero. Why is the kinetic energy zero? It is zero because its velocity is zero. The total energy of the object is thus mgh. As it falls, its potential energy will change into kinetic energy. If v is the velocity of an object at a given instant, the kinetic energy would be half mv square. As the fall of the object continues, the potential energy would decrease while the kinetic energy would increase. When the object is about to reach the ground, h is equals to 0 and v is going to be the highest. Therefore, the kinetic energy would be the largest and the potential energy will be at least. However, the sum of the potential energy and the kinetic energy of the object will be same at all the points. That is, potential energy plus kinetic energy is equals to constant, or mgs plus half mv square is equals to a constant. The sum of kinetic energy and the potential energy of an object is its total mechanical energy. We find that during the free fall of the object, the decrease in potential energy at any point in its path appears as an equal amount of increase in the kinetic energy. Here, the effect of a resistance on the motion of the object has been ignored. There is thus a continual transformation of gravitational potential energy into the kinetic energy. So we are coming to activity 10.15. An object of mass 20 kg is dropped from a height of 4 meter. Fill in the blanks in the following table by computing the potential energy and the kinetic energy in each case. So these are the tables. Think it over. What would have happened if nature had not allowed the transformation of energy? There is a view that life could not have been possible without transformation of energy. Do you agree with this? So, students, we are doing the live reading of Work and Energy chapter of grade 9 science. 10.3 Rate of doing work. Do all of us work at the same rate? Do machines consume or transfer energy at the same rate? Agents that transfer energy to a work at different rates, let us understand from the following activity. Activity 10.16. Consider two children, say A and B. Let us say that they weigh the same. Both start climbing up a rope separately but reach a height of 8 meter. Let us say A reaches takes 15 seconds while B takes 20 seconds to accomplish the task. What is the work done by each? The work done is the same. However, A has taken less time than B to accomplish that work. What has done more? Who has done more work in a given time? Say in 1 second. A stronger person may do certain work in relatively less time. A more powerful vehicle would compete complete a journey in a shorter time than a less powerful one. We talk of the power of the machines like motorbikes and motor cars. The speed with which these vehicles change energy or do work is a basis of their classification. Power measures the speed of work done. That is how fast or slow work is done. Power is defined as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time t, then power is given as power is equals to work by time, or P is equals to W by T. The unit of power is watt in honor of James Watt 1736 to 1819, having the symbol of W. 1 watt is the power of an agent which does work at the rate of 1 joule per second. We can also say that force power is 1 watt when the rate of consumption of energy is 1 joule per second. 1 watt is equals to 1 joule per second, or 1 W is equals to 1 J by S. We express larger rate of energy transfer in kilowatts or kW. 1 kilowatt is equals to 1000 watts. 1 kW is equals to 1000 W. 1 kW is equals to 1000 joule per second. The power of an agent may vary with time. This means that the agent may be doing work at different rates at different intervals of time. Therefore, the concept of average power is useful. We obtain average power by dividing the total energy consumed by the total time taken. Example 10.7. Two girls, each of weight 400 Newton, climb up a road through a height of 8 meter. We name one of the girls as A and another as B. Girl A takes 20 seconds while B takes 50 seconds to accomplish this task. What is the power expended by each girl? So one is power expended by each girl is A, weight of the girl is mg is equals to 400 Newton, displacement or height is equals to 8 meters. So time taken is 20 seconds. From equation 10.8, P can be calculated as this, work done by time taken. So putting the values, you'll get the answer as 160 watts. Part 2 of the same question, power expended by girl B, weight of the girl mg is equals to 400 Newton, displacement is 8 meter, time taken is 50 seconds. So P will become 64 W. Power extended by girl A is 160 W, whereas by B is 64 W. 10.8. A boy of mass 50 kg runs up a staircase of 45 steps in 9 seconds. If the height of each step is 15 centimeter from find his power, G has to be taken as 10 meter per second square. Solution, weight of the boy is mg. So 50 into 10 is equals to 500 Newton. Height will be 6.75 meter after conversion. Time taken to climb is 9 seconds. So from equation 10.8, power is equals to work done by time taken. So it will be mgh by t. It will become 375 W. So power is 375 W. In text questions 4, question number 1, what is power? Question number 2, define 1 watt of power. Question number 3, a lamp consumes 1000 joule of electrical energy in 10 seconds. What is its power? Question number 4, define average power. Activity 10.17, take a close look at the electric meter installed in your house. Observe its features closely. Take the readings of the meter each day at 6:30 a.m. and 6:30 p.m. Do this activity for about a week. Hi, the one who has joined now. Do this activity for about a week. How many units are consumed during daytime? How many units are used during night? Tabulate your observations, draw inferences from the data, compare your observations with the details given in the monthly electric bill. One can also estimate the electricity to be consumed by specific appliances by tabulating their own known wattages and hours of operation. So, with this, we are done with the reading of Work and Energy chapter of class 9 science NCRT. Let's finish with the summary. So point number 1, work done on an object is defined as the magnitude of the force multiplied by the distance moved by the object in the direction of the applied force. The unit of work is joule. 1 joule is equals to 1 newton into 1 meter. Work done on an object by a force will be 0 if the displacement of the object is 0. Next point, an object having capability to do work is said to possess energy. Energy has the same unit as that of the work. An object in motion possesses what is known as the kinetic energy of the object. An object of mass m moving with velocity v has a kinetic energy of half mv square. So, next point, the energy possessed by a body due to its change in position or shape is called the potential energy. The gravitational potential energy of an object of mass m raised through a height h from the Earth's surface is taken by mgh. According to the law of conservation of energy, energy can only be transformed from one form to another. It can neither be created nor destroyed. This we already know. The total energy before and after the transformation always remains constant. Energy exists in nature in several forms such as kinetic energy, potential energy, heat energy, chemical energy, etc. The sum of the kinetic and potential energy of an object is called its mechanical energy. Power is defined as the rate of doing work. So SI unit of power is what? 1 W is equals to 1 joule per second. So students, with this we are done with the live reading of chapter number 10 of grade 9 NCRT science book, and the name of the chapter was Work and Energy. In case you are interested in hearing the audio of the previous 9 chapters, you can come to the playlist of my YouTube channel, and there you can find all the 9 chapters. Stay connected. See you in next video. Thank you.